So we're taking a look at general properties of exponential graphs. And there are two types of graphs that we're going to study. One is exponential growth, and the other is exponential decay. And you can see that the difference between these is that if I'm going to write it where a is greater than 1, then it's going to be a negative exponent for the decay and a positive exponent for the growth as far as how the function looks. Now, once we actually plug in numbers, suppose I pick a number like if a is 2, then this graph is going to look like a to the x is 2 to the x. So we end up with y equals 2 to the x. And if we choose something like a is 2 for this one, then we have y equals a to the negative x, which is 2 to the negative x, which is actually the same thing as 2 to the negative 1 to the x, which is the same thing as 1/2 to the x. So more commonly, rather than using this notation that you see highlighted over there already, I would really be looking at when you don't have a negative exponent, is the number that's the base going to be a number bigger than 1 or a number that's between 0 and 1? So for these, we have between 0 and 1 for the base. And for this, we have a base that is greater than 1. And that just has to do with multiplying. Does multiplying by something make it grow or shrink? If we multiply by something bigger than 1, it makes it grow. If we multiply by something between 0 and 1, it makes it decrease. So let's take a look at some general features of exponential growth. The domain will be all real numbers because we are able to plug anything in to the function right there without causing any division by 0, without causing any square root of a negative or anything like that. The range, however, is only that y is equal to 0 because no matter what I plug in for x, and this is a little easier to think of honestly with our numerical example that's off to the side over here. No matter what you plug in for x, you're always going to get that we get a positive out. If I plug in a negative, then I'll get a fraction like 1/2, 1/4, something like that. If I plug in 0, I get a 1. If I plug in a positive, I get a positive number bigger than 2. So regardless of what I'm plugging in here, then we're going to end up with a positive number, and I'm never going to get a 0. And you can also see this visually. This graph right here never crosses below the x-axis. It never goes into negative y values. And so therefore the range is that y has to be 0. Now, if I wanted to write these in interval notation, all real numbers would be negative infinity to infinity, and the range would be 0 to positive infinity. The y-intercept is the same for both of these graphs at 0, 1. And I notice that if I picture myself sort of walking along this graph from left to right, I am going up the entire time, so it's increasing. Also, there is a horizontal asymptote at y equals 0 because as I approach that, as I go off to negative infinity, my 2 to the giant negative number, or whatever my base is to the giant negative number, is going to get closer and closer and closer to 0. And I am able to draw this without picking up my pencil, so we're going to informally call this continuous. So now let's compare that to this guy right here. A lot of these qualities are going to be the same. So for example, we're still able to plug any value in to the exponent, and therefore my domain is still all real numbers. I'm still never going to get any negative outputs, and I won't even be able to get a 0. So therefore, my range is that y has to be greater than 0. And we can also remember, think of that graphically as we're always up in this positive part of the y values. It's never going below into the negative y values. The y-intercept is still always going to happen at 0, 1. And as we walk along this function from left to right, we are going down. Therefore, it's always decreasing. And we also have a horizontal asymptote at y equals 0. This time as we go off to positive infinity, I'm going to get closer and closer to y value outputs of 0. And finally, I still can call this continuous because I can draw a sketch of it without picking up my pencil. So let's take a look at the little question at the bottom here. Recalling our work with function transformations, how would the graphs of y equals a to the x and y equals a to the negative x, where a is a fixed positive number, how would these two be related to each other? And I just want to point out that if we have something like this and we want to do a reflection over the y-axis, then we take the place that is sort of inside the function, which is right here, and we make that into a negative. So the reflection over the y-axis will be created by changing the sign. Now, if I were to change the sign outside, then this would be a reflection over the x-axis. So that's not what we're dealing with here. This is what we're dealing with here. We have a reflection over the y-axis. And if you look at these two functions, you can kind of see how we do have that reflection going, don't we? We've got, I'm trying to not go crooked on you here. Okay, there we go. We've got these two functions, and if you can picture reflecting right over, and I'll put it in red, right over that y-axis, like put a mirror there, and you're going to get this guy as a result. All right, we're going to turn the page and go on to the next video for the 4th page of the 3.1 notes, where we start talking about how we can use the one-to-one property to solve exponential equations.